All right, factoring special products is what we're talking about today. So we talked about multiplying special products um, a couple of weeks ago now, but so this is just the opposite. So just a quick review of multiplying special products. We found that they have um, kind of shortcuts. So you can use the box method, absolutely. Um, but it's also helpful to be able to recognize these things and save yourself some time. So when you have a minus b squared, that always turned out to be the pattern a squared minus 2ab plus b squared. With the addition in the middle, the only difference is that it'll be plus 2ab instead of minus 2ab. And this is the one I found the most helpful. When you have one of each kind, this is called a difference of squares, and we'll end up with a squared minus b squared here. All right, so now we're going to talk about how do we go the other way. How do we start with one of these and go backwards into our factored set of binomials? So factoring the difference of squares. This is the one that I think is the most helpful to recognize. If your two terms, there's no middle term, and your two terms you have left are perfect squares, then it's pretty easy to factor it because you're just going to square root each and have one set with addition and one with subtraction. So for example here, I have x squared minus 25. So absolutely you could say I want factors of negative 25 that add to 0. And you could do it the way we've been talking about in our last two sets of notes. What I think is easiest when you see this set of two perfect squares is to just recognize that they're a difference of squares. So this would be x minus 5 and x plus 5. The square root of x squared is x, the square root of 25 is 5, and you want one of each symbol. Because negative 5 and 5 add to 0 and multiply to be negative 25. Now, the reason I kind of would prefer, and I think it's easier to just recognize a difference of squares and get in the habit of doing it this way instead of the longer way, is not everyone always remembers that that middle term is 0. So sometimes we make small mistakes that way. So same thing here. 1 is a perfect square, 9 is a perfect square. Any exponent that's even is also a perfect square. If it's odd, it's not a perfect square. So it also would be helpful to know what your perfect squares are. So if you need to make a list, you can always do that by multiplying the same number times itself. Like 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. You have 16, 25. I think knowing the first 12 perfect squares is really helpful. So I'm going to write the first 12 here for us. And if you know your times tables, generating a list is usually pretty easy. But 1 is a perfect square. The square root of 1 is 1. 9 is a perfect square. The square root of 9 is 3. And then the square root of x to the 10th is x to the 5th. So you just take that exponent and divide it in half. And then I want another set where you're subtracting. Okay? And they're factored. So let's do a couple more examples. Again, you need to verify that they're perfect squares. 16 is a perfect square, so is 4. And then as long as your exponents are even, they'll work as well. So the square root of 16x squared is 4x. The square root of 4y squared is 2y. So we need one set that's subtraction and one that's addition. All right, here p to the 8th will work since it's even. 49 is a perfect square and 6 is even, so that's fine as well. So p to the 8th, the square root of p to the 8th is p to the 4th. Square root of 49 is 7. Square root of q to the 6th is q to the 3rd. So we need one with addition and one with subtraction. Okay, and we're done. So now let's talk about the other kind. So this was a difference of squares. We also have perfect square trinomials is what they're called. So a squared plus 2ab plus b squared, or this could also be a subtraction sign here, depending on the type. So for here, you would want to check and see if your first and your last terms are perfect squares. The middle term would be double whatever the square root of those multiplied together is, which is a mouthful. But here my square root of x is x, my square root of 49 is 7, and then if this is double 7x, then it's a perfect square trinomial. So 7x doubled is 14. So that means it is a perfect square trinomial, and I can do x minus 7 squared. And I want to do minus because of this minus. Okay, so here my square root of 9x squared is 3x. My square root of 4 is 2. So multiplied together, that's 6x. Double it, that is 12x. So it is a perfect square trinomial. So I can do 3x plus 2 squared. Okay, and especially on this one, it would save you a lot of time if you recognize that it's a perfect square trinomial over using the box method because the leading coefficient isn't 1. But if you don't recognize it right away, that's okay too. The box method will still work for you. And then same here. I know that -7 times -7 would multiply to be 49 and add to -14. So I could do the other method pretty easily. This one I think is a lot harder to recognize right off the bat, but it will save you some time if you can recognize it when you're factoring these types of problems. So here the square root of 16x squared is 4x. The square root of 1 is 1. 4x times 1 is 4x. Double it, that is 8x. Okay, so this would be 4x plus 1 squared. Here the square root of x to the 6th is x to the 3rd. Square root of 25 is 5. If you multiply them together, that's 5x cubed. Double it, that is 10x cubed. So this would be x cubed minus 5 squared. And again, I'm using minus because of this minus. Okay? And this only works if your first and your last terms are perfect squares. If I had something like 12, that's not a perfect square, I would have to do my normal factoring methods. So here it says determine if the trinomial is a special product. If so, factor it. So this is kind of what we were already doing on our last couple of slides. The square root of 9x squared is 3x. Square root of 4 is 2. If I multiply these together, I get 6x. And if I double it, I would actually need a minus 12x here instead of a negative 6x. So this is not a special product. Now that doesn't mean I can't factor it. I just can't factor it with one of my two shortcuts. And it says if so, factor it. Since it's not, we're not going to factor it, but we probably could. So for this one, we would be looking for factors of 36, because 9 times 4 is 36, that add to be negative 6, and we could factor it that way. But it's not a special product, and it said if it wasn't, then we didn't have to factor. For this second one, square root of x is x, square root of 4 is 2. Multiplied together, that's 2x. Doubling it would be 4x. So it is a perfect square trinomial, and we'd have x plus 2 squared. Here, we have a difference of 2 squares. So we just have to verify, since it's only the two terms, that they're both perfect squares. So 16 is a perfect square. X squared, since it's even, is a perfect square. 4 is a perfect square. But this y to the 5th, since it's odd, it's not a perfect square, which is going to make it not a special product. And then because it's not a special product, we don't have to factor it. And that's really only going to be for today's assignment. If it wasn't a special product, normally we would just factor it using one of our other methods we've talked about previously that sometimes take a couple more steps. And last one, I have difference between two squares again. X squared is a perfect square. 50 is not, though. The closest we could get is 49. 7 times 7 is 49. But 50 is not a perfect square. So, same reason. Not a perfect square, not a special product. All right, so for most of these, we didn't factor them if they weren't special products today, but a lot of them are still factorable. So we'll talk more about how to decide if something is factorable on Friday. And then even if it's not factorable, there's still what we call solutions to the majority of these, which we will tackle with quadratic formula even a little bit later. So just know that we have several methods under our belt now. Most everything we do will be factorable, but we can even solve some things that are not factorable when we get into quadratics, which will be how we wrap up the end of our year. At this point, you do have a Delta Math assignment to work on.